Okay, these next few slides are going to be talking about something called simple linear regression and also correlation. And this is chapter 11, and we really do chapter 11 because we need you to fully understand some of the chapter 11 concepts before we go into chapter 12, which is where the real meaty material is. So you have all been exposed to a simple linear regression model. You probably saw it in the past as follows. You probably saw it as y equals mx plus b, where that lowercase b is the intercept and where m is the slope. In more scientific notation, not literally, but the notation that we would use here is we'll have y, which sometimes we call y the response, is going to be some constant, b naught, so that would correspond to b here, plus beta 1, so beta naught plus beta 1, so beta 1 corresponds to the slope here. So you can kind of think of it that way. We'll be using the least squares method, which you probably have heard of or maybe even done in the past, to estimate these values of beta naught and beta 1, just like we use x bar to estimate mu, and just like we use s to estimate sigma. Now we're going to be using beta naught hat to estimate beta naught and beta 1 hat to estimate beta 1. Now, these are the equations that you're going to be using, that you'll be using to compute these values. However, I'm never going to ask you to actually crunch these numbers. Now, there may be an occasion in the homework problems. Sometimes the homework problems, are multiple parts. And sometimes I like 2 of the 4 parts or 3 of the 4 parts. And I don't have a way of picking and choosing, just do A, B, and D or whatever. So it's possible that you might need these equations. So that's why I have that in there. And as a matter of fact, I'm going to scoot ahead here. If you go to, let's see, which slide will it be? It would be the very last slide, just so you know. I have got for you, let's do the very last slide, the second. Yes, the second to last and last slides in this slide set. And I want to show you this. So this is the second to last slide here. So these are equations you may need for homework, but not for quizzes or the exam. And then this is the last slide, and these all have links. You'll have to go through the actual PowerPoint to get to the links. But I have how-to videos that I found. I didn't make these. I found these online because they were done, very well. So I don't want to reinvent the wheel. Anyway, so just remember when everything is done here that that this slide here, the second slide, and then the second to last and last slides also have some information on them that you might find pretty helpful. Okay, so suppose we want to model some data. We think our data has a linear, that there's a linear relationship between X and Y. How are we going to do that? Well, this is what our fitted regression line is. Now notice the actual model, I'm using capital letters to represent the actual values, and I'm going to be using the lowercase here to represent specific points that we take from a sample. So what we're going to be doing here, if we look at that second slide, this N right here, that's going to be the sample size. So we're going to be taking a sample just like we have in all of the other hypothesis testing we've done. So this is my sample size of N. And just like with any other sample size, the bigger it is, the better the estimates. Okay, so this is going to be my fitted or regression line. So we're going to have my estimate of the intercept, my estimate of the slope, and then we're going to have xi. So the xi and the yi, well, that should be a lowercase right there. These are the values of the actual observed data. So those are real values. And when I punch those into this equation, once I figured out what beta naught hat and beta 1 hat are, then I'm going to have this, they're not necessarily going to be a perfectly equal. So EI is what we call a residual, R-E-S-I-D-U-A-L. You can also think of it as the error, but I'll refer to it as the residual for any particular observation. And so the way we get the residual, and this is going to play a pretty important role in both chapter 11 and chapter 12, what the residual is in words. So let me write this equation in words. So the residual equals the actual data point y that we see minus the estimated data from the model. And the way we're going to get yi hat, that's just going to be this equation without the error in there. So this is going to be the actual data yi, and this is going to be estimated data yi hat, which is based upon this equation here. And depending upon the behavior of those residuals, they can sometimes tell us whether or not a linear model is a good idea or a bad idea. We can also have confidence intervals, just like we had, we had confidence intervals on mean, we had confidence intervals on the variance, we have confidence intervals on the ratio of two variables. We can do confidence intervals on any population parameter. We can also do it on my, again, intercept. Sometimes you call it the constant as well, intercept and slope. And these are the equations. Here's what's nice about these equations. I do not expect you to have to plug these in at all. So I'm going to show you how to, we will use Excel to get my lower and upper bounds on both my slope and my intercept. So that's what's really great about that. We're also going to be doing a hypothesis test on the slope for our model. So remember that our linear model, I'm having some issues here with my markers as usual. And of course, my neighbor's dog is barking, of course. So this is going to be my model. Remember, my model is y equals beta naught plus beta 1 times x. And there are two hypothesis tests that we're going to do. This is going to be a hypothesis test on the coefficient on x. So this would be the hypothesis test on the coefficient beta 1, which is also the slope. I mean, we already know this. And this is a hypothesis test on what we call correlation. So correlation, or correlation coefficient, technically it's called, that is the Greek letter rho. Now, this is also called, so whenever, just know this is only good for simple linear regression, right? So a hypothesis test on the slope and a hypothesis test on the correlation, and they're both considered and called something called a significance of regression test. This is only, we can only say that these two hypothesis tests are the significance of regression test for a simple linear model. And you'll see what I mean when I get into multiple linear regression in chapter 12. So just like with any other hypothesis test, we're going to reject the null if my p-value is less than alpha. For each of these hypothesis tests, we will have a test statistic that is T naught. They will both have n minus 2 degrees of freedom. And these values here, again, these are all on those equation pages that I mentioned a couple minutes ago. So I don't expect you to have to compute this, and I don't expect you to have to compute this. And as a matter of fact, R squared, I didn't even tell you what that is. That's to come, but this is called the coefficient of determination, and I'll talk about that in a minute. And again, I don't really need you to know this. You do need to know that it's a T naught test statistic, though. That is going to be important. So if I fail to reject H naught, what that means is I'm going to assume that beta 1 is equal to 0 here, which means there is no linear relationship. So we're going to assume that beta 1 is equal to 0. If we reject H naught, that means we're going to say, okay, the slope definitely isn't equal to 0. So beta 1 could be, it could be positive, should have said just bigger than 0, or negative, but it's definitely not 0. So whenever we reject H naught, it means we really don't have a good linear relationship. And you can usually tell that really just by plotting y as a function of x. Okay, so what is this coefficient of determination that I just mentioned? Well, that's on the next slide. And this is a measure of how good your model is. So we like our R and R squared values to be quite high. So R squared is what we call, and I like this definition of it, is the fraction of variability that can be accounted for by the model. So the bigger the R squared value, and also its square root, R is actually the estimate of rho. I could say that R is just equal to rho, my estimate of rho. Both of these values are going to be between 0 and 1. Wait, let me think about this. I might have this actually wrong. I actually do. Hang on a second. I need to make a little adjustment here. Yes, I definitely meant to make these zeros a 1, and I'm just catching this now. Let me use a black pen here. So please make this change, and I'll fix the slides. That should be a -1, and this is a -1. So you can have a correlation that is negative and an estimate of the correlation that is negative. The point of this, and our Excel output is going to show us this. I'm going to show you how to do this in Excel shortly. What we got here is we'd like a value of 0.7 or higher for this R value. Now you can, it doesn't mean it is a bad model if it's less than 0.7, but a 0.7 R value means that we have a pretty good fit to the model. That means my correlation is pretty strong. So we kind of like to see that a little bit higher anyway. Okay, then what we're going to do is, so once we have this model and we've got beta naught hat and beta 1 hat, what we want to do is we really want to see if it's a good model, because I can come up with I can get a beta naught and a beta 1 hat for any data set that I want, but is it a good model? So this is one way to determine if our model is good, by using R squared and the correlation. The other thing we want to do is take a look at these residuals, which I mentioned. And the residual, again, remember, is what we actually see. So this is actual minus predicted, or model predicted. So if we can also call it error analysis. So there are 3 properties that we'd like to see with these residuals, these EIs. The first is we would like to know if we made a histogram of them. So these bars are like a histogram. We would like the histogram to look like a normal distribution. So here you can see there's kind of a fake normal curve here, but this is a pretty good looking normal histogram. The second thing we'd like to see is that our residuals have constant variance. So if I plot my residuals, these EI, and then if my x-axis is either the individual xi's or the yi hats, these are the types of things that we can see. And the one that we want to see this. This is right out of the book. So this shows that we have constant variance. It's not getting bigger. It's not cycling here. It's not doing this kind of weird like sine cosine wave thing. So if we plot our residuals like this and we see something that looks random, we don't want to see this. We don't want to see that. We don't want to see that. That's what we hope for. And then finally, we would like to see, so here's an example this is another example of my predicted values against the residuals. And then what we would also like to do is we'd like to know that our mean residuals are equal to 0. And you can kind of see that, I'm using this here also, you can kind of see that if I were to average all of these values of my residuals, that it's going to come out pretty close to 0. So that's my point. So if I took, and I said, in other words, if I took the sum over all of I, so I'll say all I, I going from 1 to n, and I divide by n, I would really hope that that would equal 0 or be approximately 0. So those are the 3 properties we'd like to see with our residuals. So now let me show you the example that the textbook uses, all right? And what they use is an example of, so my dependent variable, or my response, which we call y, that's going to be the purity of something. So that would actually be in percent as a function of hydrocarbon level, all right? And they took a sample here, a sample of size, 20. So here we have a sample of size 20. And what they did was they plotted all of the y's and the x's. So again, this is, you know, my y-axis, this is x. And then this is the fitted line. So if we, this fitted line right here, that's what's going to be what we call y hat equals beta naught hat plus beta 1 hat times x. That's what the equation of that line is going to be. And this is my hypothesized model. Now, you can put this data into Excel. And again, the last slide of this set has a link to show you how to do simple linear regression in Excel. And I will have done that in class as well. And when you do it, this is the output that you're going to get from this data. So the next slide is what the Excel output is right here. Now, you would only fit a linear model if you first always plotted. If this data went like this, or like, you know, I don't know, something else, if it doesn't look linear, then don't fit a linear model to it. But this looks pretty linear, so it's definitely a good try. So this is what I'm going to get when I do my test of hypothesis. Remember, first I'm going to do the test of hypothesis on the regression, and I wrote this before, coefficient on x1. So I'm going to refer you back to where I wrote that down, the coefficient on beta 1. I wrote that once before. So the regression coefficient beta 1, that's my hypothesis test here. But it also is exactly what I'm putting here. I'm also testing at the same time, even though it doesn't show, I'm testing to see if my correlation or a measure of how linear x and y are, do they have no relationship that's linear, or do they have some sort of a linear relationship, whether or not it's positive or negative? By the way, when rho is less than 0, it means that we would have a negative slope. That kind of makes sense. It means that as x gets bigger, y gets smaller. And when rho is bigger than 0, then we have a positive slope. And guess what? You would have known that also if you had looked at beta 1, right? So same thing. I should say beta 1 hat here. And well, let me take that off. Changing my mind here. Okay, so remember, for a simple linear regression model, and I'm going to highlight both of these. For a simple linear regression model, both of these tests are also referred to as the significance of regression. That means, is the regression significant? Is there a linear fit? Look what else we've got here. We have things called multiple R, R squared, and adjusted R squared. The two that, well, the one that you're going to need for homework is going to be this value right here. That is what we call R squared. Remember, we said we would like R squared and R to be pretty big. So that is a pretty good number for R squared. Adjusted R squared, sometimes that's written this way. That's what you would actually use in practice. So I kind of wanted to be clear about that. But what you need for the homework questions is when they ask you for what the coefficient of determination is, that's what R squared is. And I'll remind you, that's called the coefficient of determination. Okay. Now, that's good. And observations is 20, that's N. Now, this is the Excel output. Now, remember, I said that there was going to be a test for the significance of regression. This is also called the significance of regression test here. right here. And you're going to notice here, this is actually an F naught test statistic. And down here, these are T naught test statistics. For simple linear regression, this is the significance of regression test, the results. But guess what? So is this. So for simple linear regression, both of these outputs here are going to be what we call the significance of regression output. So what I'd like to do is to go back on remember which slide number it is. I forgot to put the slide numbers on here. If you would go back to this slide here about the significance of regression, it shows up right here in Excel really as a test on beta 1, but it's also a test on the correlation. We called it the significance of regression test. And I said, if you're going to do these two hypothesis tests, it's going to generate a test statistic that is T naught. That's exactly what this test statistic is here. And in fact, for this particular problem, my test statistic will actually be this 11 value. Now, another thing I want to point out is when you're doing a significance of regression test, I'm going to put it right in the middle here. So we can also create an F naught test statistic for significance of regression. So we've really got three test statistics going on here. We've got a T naught if you're looking at the slope. We've got a T naught if you're looking at the correlation. And we've got an F naught if you're just looking to see if there's any relationship at all. What is interesting about this, and I'm trying to give you a lot of information here all at once, that's my test statistic for significance of regression. But see where it says significance F here? Do you know what this is? This is actually the p-value for a significance of regression test. And notice that if I had expanded this column here, this 1.2273 times 10 to the minus 9th, guess what? That is exactly this value right there. So these are equivalent values. So they're both the same p-value because they're testing the same thing. So significance of regression is testing this, and that p-value right there is associated with, guess what? P-value for this test, that's going to equal, I'm just going to use this notation, 1.23 times 10 to the minus 9th. And guess what here? How many times I'm going to say guess what here? P-value equals 1.23 times 10 to the minus 9th. They both have the same p-value. Because the p-value is so small, we know that we're going to reject H naught and conclude that there is a linear relationship. So I'll write this over here. So because the p-value is less than alpha, no matter what I pick for alpha, right? I didn't even pick an alpha. So remember, alpha is usually 0.01 or 0.05. That is the p-value, that 1.23 times 10 to the minus 9th is way, way smaller than those, right? So because the p-value is small, we're going to reject H naught. So that's going to be my conclusion. And my inference is going to be that, purity, which is that Y, and hydrocarbon level, which was X, have a linear relationship. And in fact, that p-value is so small that I would even put the word strong before relationship, have a strong linear relationship. Okay, what else have we got here that we can pull out? Okay, great. We know that they're related linearly, but now what is my final model? So my final model, that is going to be identified here by looking at these values right here. So wherever it says coefficients, that's going to be whatever my hats are. So this intercept, that's associated with beta naught, and X is my beta 1. So this stuff right here, I can see that beta naught hat, and that's why I said Excel will do all that least squares stuff for you. Beta naught hat is going to be 74, and I'm going to take it to 4 decimal places, 0.2833, and beta 1 hat is going to be 14.947, what is it, 9475, right there. And so my final model here, that's going to be, I kind of want it to stand out a little bit more than that. Let me use this pen. The final model, I'll do it in black. Y, the purity, is going to equal, and this is actually Y hat, is going to equal 74.2833 plus 14.9475 times X. And that's going to be my final model. Okay, next what we have to figure out is it a good model? So one of the ways we can see if it's a good model, something that we definitely like, we like that this R squared value, and if I took the square root of it, it's going to be like quite high, actually. This is high, so we can see that R and R squared are bigger than that 0.7, so that is a good thing. So I'm going to put a smiley face right there. Okay, we like that. Now we're going to do that residual analysis. So that means we're going to take a look at what we actually saw versus what we saw, and then versus what the model predicts. So that is the next slide. So here is my residual analysis. So what I did for this model was I took a look at, so here's the observation number. Here's X, here's Y. So this is what I actually saw. That's Y, this is Y hat. And what is that? Well, that's the model that I just created. So what I'm going to do is plug in X into my final model. So the final model said that Y hat is equal to 74.2833. Remember, this is the final model. 74.2833 plus then the slope 114.9475 X, and that generates this column here. So for example, this 94.612, how do we get that? That is 1.36 times 14.9475 plus 74.2833. Maybe that's something I should do here. Let me just grab one of these here. Let's take this guy right here. And let's just take him over here. And how do we get that? That is going to be 74.2833 plus 14.9475 times the X value associated with that, which is that 1.36. So I've generated my YI hat. Then this is the residual. Remember what the residual is? We're going to say that's E sub I or E sub J, and that's going to be what I actually saw, which is this column, minus what my estimate is here from my model. So let's pick one over here where you can see it. This one, this minus 1.56. How do we get that? That is equal to Y, which is 93.65, minus 95.21. So it's Y I minus Y hat. Y specifically, Y10 minus Y10 hat. So I'm going to generate these residuals here. Now, there are three things we said we like about residuals. We want them to be normally distributed, we want them to have constant variance, and we want their average to be close to 0. Well, let's start with number 3 here. If I average everything in this column, this is what I got for the average right there. You could call this, if you'd like, this would call it E bar if you'd like. That is the sum of all the EIs, I going from 1 to n divided by n, and n was 20. Make sure you know that, okay? So that's pretty close to 0. So my third criteria is pretty good here. Let's go over here. Normally distributed. I have 20 data points. So I decided to use 4 bins. If I took the square root of 20, I'm going to get something between 4 and 5. So I picked 4 bins and I made my bins equally spaced here. So these values here are the values of my residuals. Okay, so this is EI, and then this is the frequency, because we've made histograms before. So if I count up all of the values in this column between -2 and -1, and you can do it, you'll see that there are I think it's 4. Is it 1, 2, 3? There are 4 values in that interval. If I go -1 to 0, I'm going to see that there are 6. And then there are 6 between 0 and 1, and then 4 again between 1 and 2. So it's not a lot of data points, but it's, you know, you could sort of make an argument that it's normally distributed. So I feel pretty good about number 1. I feel good about number 3. And then this constant variance. Well, remember what we said, we want to make sure that the variance doesn't look like it's trending up, or it's trending down, or it's getting bigger, or it's getting in a cycle. So we said that we would like to have on this side, we would like to see constant variance that looks something like this. And when I plot my residuals in this column, all 20 of them, this is what I get. It looks like that. So this is the Y, I hat, and then this is the E, I. So for example, let's just let's look at the last data point. If I look at the last, was that the one? Is that the last data point? Let me think here. 20 against the predicted values. Well, you know what? I think I have a different example here. No, I really don't. Anyway, if you plot the residuals, that's what you get. And they definitely don't look like they're not going up and bigger. They're not starting big and going smaller. They're not going ziggy-zaggy like that. That's what it looks like. So we like what the residuals look like. So here's my summary from the example data that was presented. All right. So the first is that when I look at, let me go back to some of these slides here. When I take a look at my data, my scatter plot appears to show, and here's my scatter plot. So that's what this is, a scatter plot. It appears to show a linear relationship here. Ignore the line. I tried to white that out and I couldn't. So if I plot Y against X, it definitely looks linear. So it shows a linear. So first thing is you do that. Then we did a hypothesis test on the we did a hypothesis test on beta 1 and on rho. Says that there, show that there is, forgot a word there, a linear relationship between purity and hydrocarbon level. How do we know that? Because we did the hypothesis test. We found that these p-values, that the p-value for beta 1 was very, very small. Now you can do, by the way, I didn't mention this, but you can do a hypothesis test on the constant too, but we generally tend not to do that. We'll just accept it as being whatever Excel tells us, regardless of the p-value. But we definitely were able to show that the p-value for either of those two hypothesis tests is very small. We reject H naught, so we have a definite linear relationship between X and Y, so that's good. Then we had R squared, and it shows that the linear relationship is strong. And what was that again? Look at the R squared value was 0.8774. It's very, very high. R squared, so we're going to put that 0.8774. And next to the hypothesis test, I want to write that the p-value was 1.23 times 10 to the minus 9th, which is definitely less than alpha. And then finally, we saw that my residuals appeared to be, again, normally distributed. We like that quality. We like it to have a constant variance. I said that was 1. Hang on. 1, 2, and then have a mean close to 0. And so a simple linear regression model does appear to be a really good model of purity as a function of hydrocarbon level. Now, the last two slides, as I mentioned, will show you some equations, again, that you might need, as I said. And then the last slide has the links about how to do some of this work. Now, one of the things I haven't done yet, which I'm going to do right now, is how you can do this t-test of significance of regression or correlation in your calculator. So I want to show you how to get that. And also, let's see, could you get the slope, intercept? Yes, and the coefficient of determination. So I'm going to go grab my calculator. Okay, I'm going to show you how your calculator can actually get a lot of the information that is right here. So there's a couple of things. There's really only one function that you need, but I'll show you both of them. So suppose that you simply wanted to you just wanted to get the estimates of beta naught and beta naught hat and beta 1 hat. Okay, so if you, oh, sorry, you can't see that. There we go. Beta naught hat and beta 1 hat. So you can get that from Excel here. They're going to give it to you in this coefficients section right here. But suppose you just want to get it out of your calculator. Now, you can only do the chapter 11 stuff in your calculator. The chapter 12 stuff you won't be able to do. So what I did is I took the original data here. And I'll let you go ahead and watch the Excel video about how to get a scatter plot in your calculator if you want to. But if I went ahead and let me show you what I did, hopefully you can see this. I think we can see it pretty good. I went into the statistics and the stat and the edit. And then what I did is I put the X values in list 1 and the Y values in list 2. Now, if I just want to generate the estimates for beta naught hat and beta 1 hat, and you're probably going to need more than that, but suppose I just want to do that, then I can go to stat, calculate, and then I'm just going to go down here to find my linear, it says linear regression function right here. So it'll give me AX plus B. So A will be the slope and B will be the intercept. So if I hit enter, and this is the old version calculator here, then I have to tell it which list to go to. So I'm going to go second function, list 1, comma, second function, list 2. And then when I hit enter, it will just generate for me these values right here. So you can see that the intercept, as we said, was going to be B. So that's that 74.2833. And then the slope is going to be represented by A, which is that 14.9475. That just gets you these. This is a pretty simple function. Now, what if I wanted to get more information that's from that, like that we would get from Excel? That's a different function. So this time I'm going to go to stat, tests, and then I'm going to scroll down until I see linear regression t-test. I hit enter. And I tell it that I put the X's in list 1, the Y's in list 2, and then I'm going to do this hypothesis test. It's always going to be a two-sided test, at least in this course. So here, notice it says beta and rho. It's testing both of these at the same time because they're going to have exactly the same p-value. And then when I hit calculate, it gives me a lot of information that's already on here. Look what it gives me. It gives me my test statistic, that t-test statistic, 11.3517. Look right there, 11.3517. It gives me the p-value, which is that 1.23 times 10 to the minus 9th, which was here and here. And it also, I really only need this function here because look, it gives me A and B. So this time it does it y equals a plus bx. So A is going to be the intercept, 74. So that's going to be beta naught hat. And this is going to be beta 1 hat. So it gives you all that. But look what else it gives me. It gives me R squared, which is that 0.877436. And then it takes the square root of that to give me R, which is my estimate of the correlation coefficient. So R is really just rho hat. So now you have a lot of tools in order to do just a simple linear regression model. And there are a lot of things that can be modeled as a simple linear regression model. Okay, hope that was helpful.